Welcome to Study Loop.
In this problem, we have a ball on a rope that is stretched taut out here and released from rest. And as it swings down as a pendulum, it then hits a pin here, so that now once it gets past this point, the radius of the cord is the length of the original cord minus this length. And so what we want to do, we want to find the smallest value for A, which is this distance here, such that the pendulum bob here would describe a circle about the peg, so that that it will actually wrap around, so that we get back up to a point here, such that the velocity is not is greater than 0, so that it actually goes around. Now, what we need to do here, again, we want to make sure that there's two things we need to make sure of, is that the velocity up here is positive, but also that the tension in the cable is still positive. Otherwise, it'll go slack and it won't be making a circle around this point. So we know that actually, if the limiting case is going to be the tension in the cable, because up at this point, to have positive tension in the cable, we need to have a velocity that's going to overcome the gravitational force. So it's going to have to be positive up here. So that's going to be our limiting case to looking at the normal force or the tension in the cable. Now, at position 1 here, both the potential and the kinetic energy are 0, since I'm measuring gravity with respect to this plane here. And down at position 2, or at some arbitrary position, or position 2 is down here, right before the cable hits this pin. Potential energy is this, and the kinetic energy is here. So we know just the velocity of the bob when it gets to this point. And now we know that the radius of this pendulum now is L, this length, minus A. And so the kinetic energy, when it gets to an arbitrary position over here, so after the cord hits the pin, we have the kinetic energy is 1/2 mv3 squared. So I said 0.3 is some arbitrary position as the bob moves through this side of the swing. And then the gravitational potential is mgy3, and we can figure out what y3 is by just looking at using the geometry here. So we're at minus a, and then we know this length is L minus a, and we can get the and then we have a negative sign here, and then we have the sign of the angle to get the vertical component. So that's the this is the height of the bob after the cord hits the peg, and it's traveled some distance theta around. Theta is measured from there. So we know that the kinetic energy, the total energy at this state, at this point here, needs to be the total energy at some other point. Of course, conservation of energy, we might as well take it at 1 since that's 0. So we know that the total energy at 3 has to be 0. And that gives us an equation we can solve for V3 squared. And we get this expression for that. Again, we're not given any numbers for this problem, other than that we start at 90 degrees here. So we do this all symbolically. And then we need to draw a free body diagram of the bob. And we can do that by basically saying, okay, we have the bob here. We're over in the region here where the tension or the normal force is in this direction. Well, actually, I defined it as positive in the radial direction. We have the gravitational force. So we have the net force acting on the bob is the force from the cable plus gravitational force. And that must be the mass times the acceleration, and the acceleration is in the negative radial direction, and it has v3 squared, its magnitude is v3 squared over r, and where r is now L minus a. we can take a dot product of this with the radial unit vector, and we rearrange some things and use this expression in here and do some simplifying, and we get that n equals minus mg times the quantity 2a over r plus 3 sine theta. Okay. So what we need for n, as I've drawn it here, we need it to be negative. So we need the cable to be pulling on the bob and not the bob pushing on the cable, because the rope can't handle compression. So that gives us our constraint, and if we look here, that's going to be it's a minimum. Again, I'm measuring I'm measuring theta from this value here. That makes more sense. Yeah. So measuring theta from here. So then when theta equals pi over 2, this we're down here. This is 1, and so we're down at minus L. Right. Okay, that makes sense. So theta from this range, from this position as I've drawn here, and I didn't look at my drawing. So we're gonna the critical point is going to be when theta equals comes back around to here, and that's 3 pi over 2. And so when the chord is when the bob is up here and the chord is the remaining part of the chord is vertical. So we look at that, and we set that equal to 0. So we have n as a function of theta, and we set that equal to 0. And we get an equation for A, and we find that A needs to be 3/5 of L. And that makes some sense. So it needs to be a little past more than halfway. Now, if it were less than halfway, then we'd have a physical problem here, because it would actually, as it came back around here, it would actually hit this pin as it went here. So the fact that it's greater than 1/2 means that it will swing and miss this pivot point here. And so we just basically find, no matter what L is, we can figure out that this pin, to get this thing to go all the way around, needs to be 60% at least of the length. The distance here needs to be 60% of the length of the cord.